This conference will now be recorded.
Hello everyone, we're starting the new chapters, that is P block elements. So here the topics today we will see position in the periodic table, that is the position of P block in the periodic table, and properties, general properties of all the elements in P block tables, metallic, non-metallic capacity of these elements, then anomalous properties of the first element, inert pair effect, and allotropism. And if time permits, after this general discussion regarding P block, we can also start group 13 elements. So this chapter, basically there are only group 13 and 14. These two groups will be finished. In 12th grade, the rest of the groups, that is starting from 15 up to 18, that are present. But in this group chapter, we have only 13 and 14, these two groups. But before starting that, we have to see the general discussion regarding P block elements. So as we are saying P block elements, first we have to know what is the position of these P block elements in the whole periodic table. So here you can see very simple picture of the whole periodic table, where we have main group. When we say main group elements, under this heading we have S. So here we have S block and here we have P block, and in between S and P block, that is in the right hand side of the periodic table, we have P block, and in the left hand side we have S block. In between these two we have these transition metals, which is basically D block. And what about F block? F block is here 4F and 5F, which is horizontally placed just below the periodic table. So our interest is only in this part, P block. And S block we have finished in the last chapter, where we have group 1 and group 2. So after group 1 and group 2, the next group is basically group 3. And in this way, it will end. That is, if you consider only D block, 3, 4, 5, 6, it will be continued up to 12. And after 12, the next group, where from the P block is starting, is group 13. Then we have 14, and in this way up to group 18. Okay. So in P block, we have total 6 groups, as you can see, 13, 14, 15. Then we have 16, 17, 18. Though in this chapter only these two groups, but here we are just discussing the general information regarding P block. So this is the position of P block in the whole periodic table, right? Now let me clear all this. So in S block, that is group 1 and group 2, why we call it S block? Because here the valence electrons, it is present in S orbital. So in group 1, we have seen the general electronic configuration, it is NS1, and for group 2, it is NS2. So you can see both in both cases, the valence electron is present in S. And then when we have D block elements starting from 3 up to 12, here electrons are gradually filling the D block as you are moving from left hand side to right hand side. That is, as you are moving from group 3 to 4 to 5, then there will be extra electron addition in D orbital. So that is why this is D block. And then we have P block. Once it is finished, that is the D block is fully filled, next there is filling of P orbital. So that is why these elements are under P block. Okay. And similar explanation, that is a similar logic is also applicable for A block, where electrons are gradually filling A orbital. So depending on which orbital is gradually filling, we have these different blocks S, P, D, F. So here we will focus on P block. So if we enlarge the P block part, here we have group 13, 14, and in this way up to 18. And what about the period? This is second period. Then we have third period. This is 4, this is 5, and this is 6. Right? Now, total 6 groups are there, as you can see, starting from 13 up to 18. Okay. Now, why there are total 6 groups? It is because if you consider P orbital, so maximum electrons you can place 1, 2, 3, then 5, 6, 1, 2, 3, 4, 5, 6. That means total 6 electrons you can fill. So when you are filling the first electron, it will be under group 13, that is boron, aluminium, gallium. Then when you are filling the second electron, now it will be 14, and in this way, maximum when you have reached, you are filling the last electron, then it will be considered under group 18. So this is the reason why we have total six groups under P block, because the maximum capacity is, it can hold electron, it is 6. So this is the reason. Fine. Now, the properties of these P block elements. So I'm talking about the general properties. We have not started any particular group yet. We are talking about the general properties. Okay. So here you can see all the 6 groups, right? And you also use some specific group name, which you can see here. Icosagens, which is from group 13. Then tetragens, pictogens, chalcogens, halogens, and inert gases. Okay. And what about the general electronic configuration? As I have said, here electrons are gradually filling the p orbital. Now, overall, if we consider the electronic configuration, then it should be NH2, NP, 1 up to 6. So NH2, this part is fixed, but the NP part, that is changing. So when it is group 13, it is NP1. Then gradually extra electrons are added, it is NP2, then NP3, NP4, NP5, and NP6. Now maximum capacity reached. And as for inert gases, maximum capacity reached, and it is fully filled configuration. So that is why inert gases, we call these elements as inert gases, okay, because they are very, that is their reactivity, it is almost nil. So that is why we call them, the name is inert gases, or we also call them noble gases. Now the first member for each group, boron is the first member of group 13. Now first member means it is obviously from second period. Then carbon, then nitrogen, oxygen, fluorine, and neon. Now, why we have mentioned specifically the first member, it is because when we will actually go into the details for each group, there you will see that the first member for each group in P block, it behaves differently from the other members of that particular group. So if I consider boron, it will behave differently for the other members like aluminium, helium, okay? So this is the reason we have specifically mentioned this first member. Then group oxidation state. Now what it means? Oxidation state can vary for P block. You have seen in case of S block, there is a fixed oxidation state. Actually for S block, when we talk about oxidation state, it is very simple. So oxidation state for group 1, we have seen only one oxidation state possible, and that is +1, because maximum 1 electron is there. So it can be removed. So how we can get any another oxidation state? And also we have seen for group 2, oxidation state is +2. This is the only oxidation state possible. But when we have P block, now the elements, they can have different types of oxidation state. Okay, so that is why if you compare their chemistry with respect to S block, obviously now the chemistry is comparatively complex and more versatile. That is, I am comparing with S block elements. They are simple because their oxidation state is fixed. +1 for group 1, +2 for group 2. So they behave similarly. But when you will see the elements of P block, 13, 14, 15, whatever group you choose, you will see that the properties differ a lot. So their chemistry is more versatile. Now, what do we mean by group oxidation state? Group oxidation state you can easily remember. First of all, it is the last digit of that particular group. So 3 for 13, 4 for 14, then 8 for 18. Now, group oxidation state is that oxidation state which is common for all the elements. But there are also some other oxidation states possible. It may not be common for all the elements. It may vary. So for see, if I choose group 15, here +5 is the group oxidation state, that is fine, but +3 is also possible, -3 is also possible. So among these members, that is the 6 to 7 members that is present here, sometimes you will see +3 is more prominent, sometimes -3 is more prominent. And as you are moving towards group 16, 17, it is becoming more, that the number of oxidation states are also increasing, right? So two types of oxidation state we have. This is group oxidation state, which is common, and you can easily remember it from the last digit. And other oxidation states are also possible. Even negative oxidation state you can see here, right? So p block elements, if we see the general electronic configuration, it is NH2NP126. Obviously, except helium, because there is no question of p. Then elements of group 18, which we call inert gases, they are having completely filled p orbitals, and that is the reason for their least reactivity. It is not that they do not react. So when we will discuss the respective group, that is group 18, though that is not in this grade, it is in 12 grade, then you can see they react only under drastic conditions, special conditions there, but otherwise they are not reactive at all. Unlike S block, some of the p block elements, they can even show negative oxidation state, and that is not something very surprising, that is expected. Why? Because when you have S block, suppose this is a periodic table, you have S block here. Now this is the left hand side of the periodic table where metallic character is maximum, and when you are discussing p block, they are basically in the right hand side of the periodic table. So when you are moving from left to right in the periodic table, the non-metallic character is increasing, so the oxidation state will be negative. That is expected, because positive oxidation state we expect from electropositive elements, and negative oxidation state we expect from electronegative, that is the less electropositive elements, right, where electronegativity's value is very high. So that is why, see, in case of 17 we have -1 state, in 16 also we have -2, here also we have -3. So this is the reason why we are getting even negative oxidation state, which we have not seen in case of S block elements. There is only positive oxidation state possible. First member of a group, as I have said, differs from the heavier members. Heavier members means from rest of the members, and with respect to the first element, obviously the other members are heavier. So that is why here it is mentioned as heavier members. So these are the some general properties of p block elements. Metallic and non-metallic character. Remember, in S block, there you have seen only metallic elements. No non-metallic nature we have seen. But now the chemistry is very versatile, and that is the beauty of p block elements, which is why? Because now you can see metallic character, non-metallic character, not just metallic and non-metallic, even you can see metalloid type of character. So metalloid character means which can act both as metals as well as non-metals. So from the color, from these p block elements, here groups are mentioned, and from the colors you can understand the blue ones, they are basically metals. Then we have non-metals in violet color, and metalloids, they are in green color. Radioactive elements, that is from group period 7. This is 3, 2, 3, 4, 5, 6, 7. So this is just for extra information. Most of the time we will restrict our discussion up to 6 period, not 7 period, because in 7 period they are mostly radioactive. From the color you can see. So for radioactive elements we don't have much information regarding their chemical behavior. So that is why discussion is only up to 6 period. Okay. So in group 13 you can see only boron is considered as metalloids, and then you have metals. Now, as you are moving from left hand side to right hand side, gradually the number of this violet part is increasing, isn't it? So why it is so? Because non-metallic nature is increasing, and that is again expected because you are moving from left hand side to right hand side, right? And when you have reached group 70, now all are non-metallic character, right? So p block is the only block which contains wide range of elements, metals, non-metals, metalloids. Even if you are thinking about D block, there also you will see mostly metals are present. Also in a block, same thing. But P block is the only block where you can see this type of versatility. Generally, when you descend a group, that is, you are moving down the group, ionization energy decreases, that we know. And that is the reason why metallic character increases. Same thing we have also seen in case of S block. Though in S block all are metals, but still if we want to compare the order of metallic character, there also we have seen down the group ionization energy decreases because of this extra addition of shell. And that is the reason ionic energy decreases. So metallic character increases. So same logic is also mentioned here. And what about when you are moving horizontally, left hand side to right hand side? Metallic character decreases from left to right. Okay, and that you can see here. Suppose you are choosing this particular period. You are moving from gallium to germanium to arsenic. So gradually, metallic character is decreasing, non-metallic character is increasing, which is clear from the color. The heaviest element in every p block group is the most metallic, and that is again expected. Though in group 17, all are non-metals, but still, suppose if we are having a question, though all are non-metals, but still, what is the minimum metallic character you can expect? It is only from the last one, which is astatine. Okay, so though all are non-metals, but still you can say that fluorine is more non-metallic than Cl, Cl is more non-metallic than Br. So that is the order. Now this change of non-metallic character to metallic character, that is actually the reason for this diversity in the chemistry of p block elements. And that depends on from which group they are. Because if you are choosing here, suppose you are choosing group 15. So in group 15, you have nitrogen, phosphorus as non-metals. Then the next two elements, arsenic, antimony, they are metalloids. Then we have bismuth, which is metal. Then when you shift to 17, now you are seeing all are non-metals. So much variety you can see here, right? So that is the unique nature of p block, unlike other blocks. Metallic nature, non-metallic nature, metalloid character, everything you can see here. Anomalous properties of the first elements from each group. The second period elements are actually the first member, right? Because when you consider first period, there is only hydrogen and helium. So actual period where you get the full length of the period, that is all the elements present left hand side to right hand side, that is actually the second period. So second period is actually having all the elements when we are talking about the first element. So first element for any group means it is from second period. So second period elements, it starts from boron up to fluorine. So boron is from group 13. That is the first member of group 13 is boron, and fluorine is the first member of group 17. In this case, that is in cases of these first period elements, we have seen that the maximum covalence possible for them is 4. That means surrounding boron or surrounding any other second period elements, maximum 4 coordination you can get, and that is because of they can use 1 2s and 3 2p. If you consider NS and NP, that is NS NP, this is NS, N may be, sorry, here actually N is 2 because we are talking about second period, 2s and then we have 2p. Now in second period, there is no d orbital, no vacant d orbital, right? Because we have never seen any 2d. So as d orbital is not present, so maximum bonding possible from these 4 positions. So that is why maximum covalence is 4. But the elements of the other periods, that is third period, fourth period, now they can expand their covalence beyond 4. So coordination number may be greater than that. 4 coordination is also possible, but they can even reach beyond that. And that is because of the presence of vacant d orbitals. If I am considering the next period, which is 3s. Now for 3s, third period also there is 3s, there is 3p, but now you also have access for 3d, which you cannot have here. So this is the reason. Now because of this vacant 3d, what happens? Suppose I am writing here 3s2 and 3p4, which is basically the configuration for group 60, right? Now this paired electron, you can unpair it and you can shift it to any of these 3d. Now because of this shift, this is position 1, this is 2, this is 3, this is 4, now 5 position. Another electron, if it is moving, then 6 position. So coordination number can increase beyond 4. So in this way, the first period elements, they are behaving differently from the other members. Okay. Now, the first period elements, they are also very small in size, right? Because we know down the group, because of extra addition of valence shell, the size increases. So they are smallest in a particular group. The first element is the smallest. Boron is smallest in the first group 13. Fluorine is smallest in group 17. Now the combined effect of the small size and unavailability of d orbital in second period, this effect influence the ability to form p-pi multiple bonds, unlike heavier members. So what happens, as you can see from these examples, multiple bond between two nitrogen, between two carbon, then one carbon, one oxygen. Now this nitrogen, carbon, oxygen, all are basically from second period. Let me write group 13, the first element boron, then group 14, the first element carbon, group 15, the first element nitrogen, group 16, first element oxygen. Now these multiple bonds that you are seeing here, you see all the elements are basically from second period. It is either carbon, nitrogen or boron, carbon, nitrogen or oxygen, which is from second period. Now because of the small size, what happens when you have here, basically we have pi bond. So double bond means one sigma bond, one pi bond. Now for pi bond, there is sidewise overlap required. Now the sidewise overlap, it will be good when it is very small in size, so they can come close to each other, and sidewise overlap is effective. And as there is no d orbital, so it is bound to form only p-pi bond. If you are thinking one p and another d, that is not possible for second period. This type of p-pi d-pi is not possible, but p-pi possible. So because of unavailability of D, we can have only p-pi, and this p-pi is also very effective because of their small size. Okay, but when you have the heavier members, that is the members from third period, from fourth period, from fifth period, now mostly you will get d-pi bonds because now they have d orbitals. So for heavier elements, d-pi mostly you will get. Now one more thing. D orbitals, obviously, they are of higher energy compared to p orbitals energy. As a result, they contribute less to the overall stability of the molecule. So suppose in one molecule there is p-pi bond formed by the second period elements, and another molecule there is third period element or fourth period element where you have p-pi d-pi bonds. But p-pi bonds when formed, then compared to d-pi this is basically contributing to the stability of molecule more compared to d-pi. Why? Because of higher energy of d orbitals. Okay, that means p-pi bond, it is possible only in second period elements. This is more effective. As you are moving downward, that is down the group, the chance that you will have p-pi d-pi. And if we consider the contribution of these pi bonds, these two types of pi bonds, to the overall stability of the molecule, obviously the p-pi will be contributing more. Now, if we summarize, what are the reasons? The factor responsible for their anomalous behavior in general. So these reasons are basically applicable for any group, not just for any particular group. Small size, so second period elements, they are very small in size. Ionization energy maximum, because downward, when we move downward, then only ionization energy decreases. That means the first member will have maximum ionization energy. Then high electronegativity. Down the group, metallic character increases. That means electronegativity decreases. So the first member will have highest electronegativity. Basically, it will be highest, not high. And absence of d orbitals in their valence shell. So in second period, there is no d orbital. Okay. The next important that is under general discussion, we have the next important topic is inert pair effect. So it is general discussion. We have not yet started group 13. Remember that. So as it is general, so here we have, you can see group 13, group 14, then 15 and 16. I have not mentioned 17 because inert pair effect is mostly observed in these 4 groups. Fine. So what happens, as we have seen, remember the slide where we have seen group oxidation state is fixed. Group oxidation state is +3 for group 13, then +4 for group 14. So in this way, it will be like this. But there are some other oxidation state possible for these elements. Now, among these other oxidation state, it may be more than one. I will just focus on one particular other oxidation state, which is 2 less than the group oxidation state. So +3, if you consider 2 less, that means it will be +1. Then with respect to +4, 2 less means it will be +2. It is +3, it is +4, right? So as we have written the 2 less oxidation state. Now why we have written so, you will understand this. What happens? First of all, I am just saying what when we say inert pair effect, because of this effect, what actually happens. Then I will go to the explanation behind that. So first here we are seeing what happens for inert pair effect. So this is group oxidation state fixed, but I have also written this other oxidation state, which is actually 2 less than group oxidation state. So as we are moving down, what happens? The predominance of this 2 less oxidation state gradually increases. So for example, if I am saying, if you are comparing boron and indium or thallium, then it is observed that as you are moving down, for these 2 elements, +1 is more, that is, it is predominant. But for boron, +3 will be predominant. Similarly, when you are considering the next group, suppose you have lead here and you have carbon. So for carbon, +4 is more prominent, but the last one, for the heaviest member, that is, as you are moving down, inert pair effect is mostly observed. Then +2 is more prominent, not +4. So this is actually the inert pair effect. The 2 less oxidation state gradually becomes more important, more stable actually. So that is why suppose you have any lead compound in +4 oxidation state, Pb +4 oxidation state. So it will have always a tendency to accept 2 more electrons so that it can be converted to Pb2+. This is the tendency. This tendency is also present for indium, thallium, bismuth. Now why it is so? For bismuth, obviously it is from +5 to +3. So what is the reason behind that? That we have to see next. So this picture, if you see carefully, here we have group 1 and group 2. That means it is S block. Now after S block, this gap, it is actually for D block. But we have not mentioned that. We have jumped to group 13 and then there is 14, 15 and so on. But in between this group 2 and group 13, there is something happening that we have to understand. So when it is second group, this is, sorry, second period, this is third period, this is second period. So when you have this period 2, then in between, there is actually no d orbital filling. It is also applicable for the next one. But what happens as we are moving down, just consider gallium or indium, that is just before gallium, in this position, 3D is just completed. This is fourth period, and when it is fourth period, then only this 3D is invert. Okay, so just before gallium, 3D is completed, just before indium, 4D is completed, just because before thallium, 4F and 4D completed. Sorry, 4F and 5D subshells completed. So because of this presence of 3D, 4D, and for the 6th period, there is even presence of 4F, that is F electrons. So because of presence of these d electrons and F and D combined, the last period we have combined. So what happens, as we know, d orbital and F orbital, their screening property is very poor, right? Now when we are considering this, suppose I am writing gallium, its electronic configuration, it will be 4s2 4p1 because it is from group 13. Then the next element, it will be 5s2 5p1, and for TL it is 6s2 6p1. Okay, now p orbital, this single electron you can easily remove and you can get this +1 oxidation state. But if you want to get +3 oxidation state for TL, then you also have to move these 2 electrons from 6s and also from 5s. Mainly inert pair effect is observed in 5th period and 6th period. This part of, okay. So as you have to unpair these electrons, then only the question of removal arises. But unpairing this 5s electron or mainly 6s electron, it is very difficult because of this poor screening effect of F electrons, D electrons. Now look at this picture. It will be more clear. So this is suppose the 6s electrons, and you can consider it for TL or lead or whatever, because when you are considering lead, it will be 6s2 6p2. For bismuth it will be 6s2 6p3. But whatever it is, 6s2 is always there, whether you have TL, Pb, Bi or polonium, right? So this 6s electron, unpairing this 6s electron, it is very difficult because of presence of 5d and 4f electrons. And there is inside xenon core, because the, if when you consider 6 period elements, the last noble gas or inert gas is xenon. So that is why xenon core is mentioned. So because of this improper screening of D and F, because there D and both are there. If you are thinking why not applicable for gallium, it is not that directly I cannot say not applicable. So maximum is for the last element, that is TL, Pb, bismuth. But as you are moving upward, it is gradually diminishing. So for the last one, it is more effective because F is also there, D is also there. So the improper screening, it is very much there. So as a result, the attraction for the nucleus for this electron, it is very high. And unpairing this pair becomes very difficult. So as you cannot unpair this, you cannot unpair it so easily. It is not possible. So that is why we call the term inert pair effect. So for TL, you can expect +1 oxidation state, that is the most prevalent, not +3. Even if it is forming any +3 oxidation state compound, there will be a tendency to gain 2 more electrons so that it can achieve +1 oxidation state. Fine. So now you can see in a better way. So for group 13, this is the group oxidation state. Then 14 +5 +6. So +3 oxidation state you are getting when you are removing all the NH2 NP1 electrons. Total 3 electrons you are removing, you are getting group oxidation state +3. But if you are only removing this one, then you are getting +1. If you are only removing NP2, you are getting +2. If you are only removing these 3, you are getting +3 oxidation state. So +4 +2, only this is related. No, don't consider the negative one. So 2 less, -2, right? So it is because of this inert nature of these NH2 electrons, right? So what conclusion we can draw in case of heavier post-transition elements? Post-transition means after transition elements, whatever elements you have, that is actually post-transition. Just have a look in the previous slide. Transition elements are finished, then you have all these elements. So they are post-transition. The group 13 to 16, it is mostly observed, though the focus is mainly on this part. Mostly we'll get problems or examples regarding TL or PB. That is the mostly where inert pair effect is observed. The most stable oxidation state is too less than the group oxidation state, and there is a reluctance to exhibit the group oxidation state. So it is not very, there is a reluctance to exhibit group oxidation state. That means if you consider PB, it should express +4 oxidation state because that is the group oxidation state. But what happens? PB showing +4 oxidation state and PB showing +2 oxidation state, this is not mostly observed, this is mostly observed. So what you can expect that it is from group 14, so +4 it should show, but actually the tendency to show is the too less oxidation state rather than group oxidation state. Here the outer s electrons, that is ns electrons. Now this ns is it may be 5s or 6s, though mostly from 6 period it is applicable. So you can consider as 6s, have a tendency to remain inert and show reluctance to take part in bonding. So when there is, that is they are in paired condition, if it is to take part in any bonding, first of all it has to be unpaired condition. It has to be in unpaired condition. But that is not possible because to unpairing these 6s2 electrons, it becomes very difficult. So that is why we call this incident as inert pair effect. This is inert pair. We cannot break this pair easily. So bonding with these electrons is not possible. The next general property we are going to discuss for p block elements, allotropism. Allotropy or allotropism, how this term we are getting, it is generated from the Greek term allos, which means another, and trop means change. That means another form with change structure. So this is a property of an element in which the element can exist in more than one physical form. Now when I'm saying physical form, it may be through the same physical state. Suppose both the physical form, they are in solid state. Allotrop 1, allotrop 2. This is solid. This is also solid. Let's take carbon as example, which is the first element of group 15. So carbon, suppose it is having 2 allotropes. Both are solid. That means their physical state is same. But though they are, both of them are solid, not necessarily their physical form, their structure, their bonding, it will be same. It may not be so. So that is the definition, where the elements exist in more than one physical form through same physical state. I'm not saying that it has to be same physical state, it may not be so, but even if they are in same physical state, then also it may be different. So different physical form, but chemical properties will be same. Physical properties are not same, because when they are in different bonding pattern structure, obviously melting point, boiling point, density, everything will differ. That means different physical properties, but actual chemical properties, that is related to number of valence electron. So valence electron we are not changing, otherwise the element itself will be changed. So chemical properties is not affected. Maybe both of them are behaving in a same chemical behavior they are showing. There may be a slight difference in the reaction condition, or suppose temperature or solvent that you are using, but mostly they will yield same type of products. That means chemical properties are same, but physical properties will differ. Okay. This term is used for elements only. Don't think it is applicable for any compounds. This is only for in the elemental form. So if suppose carbon is from P block and allotropism is very much observed in carbon. But if you have any carbon compound, suppose you have acetylene C2H2 or you have methane, if you are thinking that methane will have different allotropes, no, that is not possible. Only the element form, that is carbon, or it is also observed in phosphorus. Only in element form, this allotropy is possible. Okay. These they are basically different forms of the same element. It happens because the allotropes are different structural modification of an element. Same element, different structural modification. But the atoms of the element are bonded together in different ways. Now, very good example we will see now is that with carbon. Carbon, 2 allotropes we will consider here, though more than 2 are there. That will be discussed in respective group, not here. Here we are just focusing on the general properties of p block. So very good example for allotrope in carbon is diamond and graphite. Now both are actually solid, but their bonding pattern is difficult. So structurally they are different. So that is the reason. Though their physical state is same, but because of this different bonding, we will have different allotropes for carbon. So it shows allotropy or allotropism. So here you can see, in case of diamond, the structure is one. In case of graphite, there are some layer structure. This is one layer, this is second layer, this is third layer, and here we have some network type of structure. And that is the reason, just a little bit I'm saying, no, I'm not going into details. Diamond is very hard in nature because of this type of network structure. But for graphite, it is slippery, it is soft, and this is because these layers can slide over one another very easily. And graphite, you know, it is present in pencil. So when we write in pencil, one layer is as if gliding over the other. So that is why we can have some mark on paper with pencil. Fine. And just like carbon, it is not just for carbon, though in carbon we have mostly the allotropes, but for other elements also, for example sulfur, phosphorus, they can also show this type of property. So as we have finished all the general properties, we will start the first group of p block, which is group 30. You can also call it boron family because the first member is boron. So based on first member, we can use this type of term, boron family. For group 14, it will be carbon family. For group 15, it will be nitrogen family. Okay. The first important thing to know is occurrence, natural occurrence, how it happens. But before that, here you can see all the elements for group 30 with their symbols. Now for boron, that is the first element, mostly occurs in borate. So this is a particular anion of boron where it is anion with oxygen. Details we will see later. Then in boric acid, H3BO3, and another some important O's. The name you should know. So for borax, this is easier to remember this formula. Na2B4O6 with 10 water molecules. This is borax. You can also write the formula like this, because why we have written so, here direct bonding with sodium, it is actually ionic, so that is why they are outside this bracket. But in general, if you write, it is easier to write total 2 sodium, then 4 boron, so it is written in this way. Then we have carnite. Now carnite, it has some similarity, only this number is different. Now isotopes of boron also present. 2 different isotopes are there. One is 10B, another one is 11B. That is a mass number. We know isotopes means number of electrons same, number of protons same, but because of difference in neutron number, N plus P, that is the mass number. P is fixed, but N is differing. That means mass will also differ. So mass is 10, one isotope, mass is 11, another isotope. And this is the abundance. So most abundant, that is actually the 11B. The next element is aluminium. Now this is the third most abundant element with respect to weight found in earth crust, and that is just after oxygen and silicon. Because it is third, so the third position, it is before it there is oxygen and silicon. Now for aluminium, there is actually different types of minerals present. So see, we have bauxite. This is the formula Al2O3. It is sometimes also represented in this way, where the number of X may vary. Then cryolite, sodium aluminium fluoride, Na3Al F6. Mica, also called muscovite. Why I have mentioned both the names? Because I have seen problems where sometimes it is mentioned with muscovite, sometimes with mica. So suppose you may get question like this, that muscovite contains which elements? So there may be in options, or it contains doesn't contain which element. So in options there will be some elements. So see which elements are present. Obviously aluminium will be present because it is mineral of aluminium. But except aluminium, there is also potassium, oxygen, silicon. Then you can also write it in this way. Then we have what it is SI. Orthoclase or feldspar, where potassium, it is not that exact formula you have to remember, but at least try to remember what are the important elements present here. Aluminium obviously there, but except aluminium we also have silicon, oxygen, potassium. Then we have corundum, which is anhydrous aluminum. So bauxite, cryolite, mica, orthoclase, corundum. The next three elements, that is gallium, indium, thallium, these three are less abundant compared to aluminium, and this one is radioactive. So mostly the discussion is up to this position, that is up to 6 periods, starting from second period 2, 3, 4, 5, 6 up to this position. You will see the discussion will be up to this position. It will not have neodymium because it is radioactive. There is not much data regarding its chemical behavior. They are so unstable. That is the reason. So these are the occurrence for group 13 elements. Then electronic configuration for group 13. So as we have seen, general electronic configuration for P block is NH2 NP 1 to 6. Now when it is group 13, it should be NH2 NP1, the first electron in p orbital. So look at this table. Boron atomic number 5, and the last noble gas is helium. So instead of writing 1s2, 2s2, 2p1, you can write it in this way. That will be easier to, not just to look at, but also whoever is writing, it is easier to write, right? So helium within third bracket, the last noble gas. So here basically we have 1s2. So total 5 electrons, 1s2, 2s2, 2p1. But if you just focus on this part, it is following this general pattern. NS2, NP1. So it is from second period. So that is why it is 2s2, 2p1. Then for aluminium, total 13 electrons. Now the configuration is neon configuration, the last noble gas. So what I'm trying to say by last noble gas, look, consider the atomic number. So if aluminium is atomic number 13, and if you already know the atomic numbers of all the inert gases, because with the inert gas a particular period ends. So when you have aluminium which is from third period, so you have to consider the previous period which is second period, and the last element, that is the noble gas in second period, that is actually neon. So neon will have these 10 electrons. So here containing 10 electrons, and rest of the 3 electrons, that will be 3s2, 3p1. So again it is following this general pattern, ns2, np1. Then as we are moving to the fourth period, it will be more complex. Now 31. Now the last noble gas, that is argon, having 18 electron. Okay. So after 18 electron, 31 minus 18 if you do, you will see there will be total 13 electrons more. So 13 electrons according to energy, first 3d will be filled, 3d 10, then 3 more electrons here. So it is always better you write it in this way. But if we focus only on this part, then it is always NH2, NP2, sorry, NP1. So for indium 49, the last noble gas is krypton. Then we have again 13 electron extra. And that is 4d10, 5s2, 5p1, and only for 6 period, that is thallium. After xenon, we will also have F electrons, 14 F electrons. So here we have F and D And for these two, we have D only. That is for gallium and indium. This is 5th, this is 6th. Then, so this N value, as you can see, the general configuration N is to NP1, but N value, it may vary 2 to 6. So starting from 2 up to 6, it may vary. 2s to 2p1 or 4s to 4p1 or 6s to 6p1, but it is always N is to NP1. Depending on from which period it is, it will vary. So here, if you look at the electronic configuration carefully, look at these points. Boron and aluminium have noble gas core. So in these two cases, you have only noble gas core. There is no question of d electrons or f electrons. Then for gallium and indium, not just noble gas, but after noble gas, there is also 10d electrons. So for gallium, it is 3d10. For indium, it is 4d10. And for thallium, after noble gas, there is 14f electrons. There is 10d electrons. So 14f electrons are from 4f orbital and 10d electrons from 5d. So this is, we are talking about the core, because this part is valence shell. But what about the core? So these points are basically related to core. Size. So whether you consider atom size, mostly discussion will be on atomic size, but you can also get ions. But we are not going into details of ions, because in case of S block, that is easier to do. Because why it is so? Because S block, you just have only one oxidation state. So it is always Na plus, K plus. So you can compare their ionic radii. But when it is P block elements, there is, suppose boron is showing one type of oxidation state, then aluminum is showing another type of oxidation state. Details of oxidation state, that will be discussed in a separate slide. But we know that they show variable oxidation state. And because of that, comparison of ionic radii, it is not so common in case of P block. So it is mostly restricted to atomic size, not ionic radii. Ionic radii, it is easier to do for S block, but here we do not have any common oxidation state. So it is not possible for us to compare, because when all are in same oxidation state, then only you can compare. Suppose boron in one oxidation state, aluminum is another oxidation state, you cannot compare their ionic radii, right? They must have same oxidation state, then only you can consider the ions and you compare the ionic radii. But as that is difficult to get, so discussion will be mainly on their atomic size. Now size, we know down the group increases, that is the expectation. But if we compare with group 2, the atomic and ionic radii of group 13 elements, better I do not write it, because as we are comparing with group 2, it is mostly the positive state, and there is not necessarily all of these will have some positive state. Okay, so better we consider only the atomic size when we are comparing with group 2. Because when I'm saying ion, it may have some anion also. As we know, in P block there is non-metals, so sometimes they can also have negative charge. Though for group 13, negative charge is not so common, but still it is better we do it only for atomic size. So after group 2, there is D block and then 13. But still 13 is in the right hand side of group 2. That means we are moving, when we are moving from S block to P block first, we are moving from left to right. So what we can expect, that atomic size, it will be smaller than those of the corresponding elements. Corresponding element means it has to be in the same period. So if you are considering boron, which is from second period, then you will compare it with lithium and beryllium. You cannot compare it with sodium because they are in same period. So that is why we are saying when you are moving from left to right. Okay. And ionic radii is not possible, because here we see +1 oxidation state, then it is +2, but this type of fixed oxidation state, that is not there, though +3 is most common. But if you consider atomic size, it is less. And even if you consider +3, then also it is obviously less, because when oxidation state increases, that means more electrons are removed. That means size will also shrink. Size will be less, right? So this is because of increase in nuclear charge when new electrons enter the same shell. Now this reason we have seen in periodic table chapter. Very basic information, not something new we are saying, but still this is the reason. So when you move from lithium to beryllium to boron, number of electrons are high. Here atomic number and the atomic number for boron, it is high. So when atomic number is high, number of protons high, that means positive charge in the nucleus is high. So it will attract the outermost electrons strongly. As a result, size will decrease. So look at this. 85 for boron. The next one is 143 picometer. But why gallium is 135? So this is actually the discrepancy. But after that, if you move to indium, it is again increasing. Thallium again increasing. But in this position, for these two, there is discrepancy. And why there is discrepancy, that we have to see. Atomic radii are expected to increase, but there is a deviation when we move from aluminum to gallium, and this is because of spore screening effect of d orbitals. When you have aluminum, there is, that is, if you consider there's a previous element, there is actually no d electrons field. Okay, so that is why no question of pore screening effect. But when you start gallium, so see this picture we have already seen. So up to this part, no intervening subshells are there. But when it is gallium, there is 10 3d electrons, and because of their poor screening property, the expected increase when you move from aluminum to gallium, that is overcome by some other effect. Another effect is poor screening effect. So the nucleus is attracting the outermost electrons strongly, and as a result, the size is decreasing. So the expected increase we are not seeing here. So this is very important information, and based on this, you can also get problems. But after that, there is no such discrepancy, it is smooth increase, right? Ionization enthalpy, though we do not have much time, but still see how much we can discuss. How ionization enthalpy changes, we know when we move down the group. That is, obviously I'm talking about the fast ionization energy. So when we move down the group, it decreases. But if you compare with group 2 ionization energy and group 13 ionization energy, so 2 is here and there is d orbital, and then we have 13. Now you know for 13 size is less, that is size is smaller compared to group 2 elements in the same period if you compare. So what you expect, that ionization energy for group 13 elements in the same period, it should be high. But actually what happens, there is some other factors operating for which the observation is actually the reverse observation. What happens? First ionization energy of elements of group 13, it is actually lower than the corresponding element. So if you consider beryllium, and after that in the same period we have boron, so for boron it will be smaller. So the reason is, when it is beryllium, basically you are removing electron from NH2, but when it is group 13 elements, I have written NSNP, not 2s2p, because it is applicable for any period. You are removing this electron. Now when you are removing NP one electron, you are achieving the fully filled configuration of NH2. So you are achieving some stable configuration. So that is why this process is easier. But when you are removing electron from NH2, in case of group 2, now you are breaking this stable configuration, fully filled, which is not, which will require more energy. Okay, so this is the reason it is lower. So in case of group 13, fast ionization energy, obviously not applicable for second. The electron has to be removed from p orbitals, whereas in case of group 2, s electrons of the same shell you have to remove, so which is difficult. Fine, so this is the reason it is lower. Down the group, expected is it will decrease, but again there is two exceptions, two discrepancies from the general trend found between these two pairs. Okay, so we'll stop here because we don't have much time left. We'll finish it in the next class. Just look at this picture. From when you're moving from boron to aluminium, ionization energy in kilojoule per mole unit, from 800 it is jumping to some value in between 600 to 500. Then from aluminium to gallium, it should decrease, but it is slightly higher. Though in picture it appears as if both are same position, but actually gallium is slightly higher. Then again it is decreasing from Ga to indium, but in this pair again there is increase, which is not expected. So these are the two discrepancies we found, but we'll not be able to finish it. We'll finish it in the next class. Okay, thank you for listening. We're ending the session here.